Well, hello, chemistry students. Let's get started with today's lesson. We're going to look at lesson 9, making solutions. So if you'll turn to your study guides and open up to lesson 9, making solutions, we'll go ahead and get started. So this is going to be a 2-part video series, and we're going to do part 1 right now. So make sure that you also watch the video on part 2. All right, so let's get started making solutions. What exactly do we mean by a solution? What is it? Well, it's a homogeneous mixture of 2 or more substances that can be either solids, gases, liquids, or a combination of the 3. Now, let's look at homogeneous for a moment and give you an example. Classical solution would be a salt solution, which is made up of salt, sodium chloride, and water. And the salt essentially is dissolved in the water, and it makes a uniform or homogeneous mixture, as you can see from this example. The key term here is dissolving. Often when we say we're going to dissolve two things to make a mixture, we're making a solution. So keep that in mind, dissolving keyword. Here's another example of a solution. Again, it's uniform throughout. This is a mixture of sugar and dye, red dye, and water. And it's a uniform mixture. Those components are all dissolved to make this sugar solution here, okay? All right, now, every solution is made up of 2 parts. The 2 parts here are listed and defined. There is the solute, which by definition is a solid, liquid, or gas that dissolved when mixed with other substances, okay? And then the solvent part is usually the substance present in the largest quantity in a solution. Solvents are usually liquids. They don't have to be. Sometimes they are gases, but most of the time, especially in our class, solvents are going to be in the liquid state or liquid form, okay? All right, what we're going to do is we're going to draw a particle diagram in this beaker of a salt solution, okay? Remember, our salt solution is made up of sodium chloride, NaCl, and water, okay? And those are the 2 components that make this uniform mixture. So what would this look like on a particle level? Well, of course, we can't see that with our eyes, but we can draw a model or a particle model that could represent what this mixture would entail or what it would look like, okay? So on the board over here, I'm going to set this up. I'm going to show you the particle diagram that I have made for this particular solution, right? So move the computer over so that you can get a better look of this. Okay. Now I'm going to reveal our solution, our particle diagram. Okay, so what I have here is my beaker, okay, set up, and I have already taken my salt and I have dissolved it in water. So sodium chloride, before it's dissolved, has a solid crystal structural pattern, okay? And I showed you salt. Actually, let me grab salt for you, a real example. If you recall, I showed you this before. This is salt crystals in the solid form. And essentially, we're going to add these solid crystals to water to make a salt solution. And a particle diagram or a particle model that's three-dimensional of these crystals would look something like this, okay? The silver ones that you see happen to be the sodium metal that's in the salt, and then the green are the chlorine non-metal atoms that are in the salt crystal, okay? All right, so here we go. Now, going to our particle diagram, what's essentially going to happen is that when our crystal structure is exposed to water, the water is going to be breaking down the bonding structure of this crystal and causing the atoms to dissolve. Now, the metal and the non-metal atoms here are actually in ion form, all right? So the metals, remember, they're cations, and so the metal, sodium, is going to be a positive cation, and the non-metal chlorine is going to be a negative anion, okay? And so that those ions essentially after everything's been done and it's been dissolved in water is going to form a particle diagram like this, okay? Let's go to our particle diagram. First of all, the salt, okay, the salt, which is made up of the sodium ions and the chlorine ions, are going to be our solute component to our solution. And the water is going to be the solvent. And typically, water usually is a solvent that we use quite a bit in chemistry, especially in this class here. Okay, remember that water is going to be in the liquid form, which we find most solvents, and solutes they can be liquids, they can be gases, and they can be solids. In this case, we're going to start with a solid structure of salt. We're going to place it in water. The water begins to break those crystals down, and what's happening is the water molecules are surrounding the individual ions that you can see right here. So remember, the green here represents the chlorine ions, okay? And remember, the chlorine ions are negatively charged. And then the silver are the sodium ions, and they're positively charged. So I'm going to fill those in. And then the water molecules are just going to completely surround those ions because there's going to be an attraction between the water molecules and these ions. And notice that for the negative charge, the water molecules, these yellow atoms are hydrogens, and the red is oxygen. And so the hydrogens are actually pointed towards the negative charge because those hydrogen atoms are attracted to that negative charge. Whereas if you look at the metal ion, okay, they're positive charged, and the oxygens, which are the red, are attracted to the positive charge ion in this solution, okay? And so, again, this is just a particle representation of showing you that ultimately what I'm trying to say here is that the water molecules are surrounding these individual ions, and when those ions are surrounded by water molecules, we say that the salt crystal has dissolved, and we create a uniform solution. Now, this may not look uniform at the particle level, but certainly at our macro level, by what our eyes can see, is it looks uniform to us, okay? Even if it's not quite uniform on a particle level, okay? So keep that in mind, all right? So there's our particle model that I wanted to show and demonstrate to you. Now, we're gonna study solutions. Let me come back here. We're going to study solutions in greater depth, later on. Okay, so this is just kind of get you a start of what solutions are and some of the component parts and so forth. Okay. All right, so let's go back to our study guide here. All right, so we just got finished with our drawing our particle model in our beaker there. So now what we're going to do is we're going to talk about a very important concept of solutions, and that is solution concentration. Now, essentially, you think of concentration is the amount of solute particles that's dissolved in a certain volume of solution, all right? And there are various ways to make concentrations of solutions, but the one that we use predominantly in chemistry is known as molarity. Molarity has basically a symbol of a capital M as indicated here. So molarity, capital M. Now, what is molarity? Well, it's the number of moles. There's our thing. When we grab our mole mascot, yep, there we are. It's essentially the number of moles of particles that's dissolved in exactly 1 liter of solution, okay? And actually really what we're talking about is the total volume of solution as indicated by our molarity equation. So in other words, to find the value of molarity here, we're going to take the moles of the solute and we're going to divide that by the total volume of solution that we have, okay? And if for instance, the solution is, or the solvent is water, then the total volume of the solution is usually the total volume of the water, okay? And so forth, as you'll see in just a moment, okay? So let me kind of demonstrate this. So if I have a beaker here, and this beaker is 1,000 milliliters, okay? 1,000 milliliter beaker, hopefully you can see that, which means that this total beaker's volume is 1 liter, okay? Now, molarity needs to be in units of liters and no other volume units, must be liter by definition, okay? So if you're given milliliters, you must convert that into liters. So I have 1 liter solution right here, okay? Or 1 liter of volume here. And I have my mole, okay? So if I take 1 mole, this is 1 mole, right? And I place the 1 mole into my 1 liter, then what is the molarity of this solution, okay? What's the molarity? Well, again, I have 1 mole in 1 liter. So if I put that into my equation, I have 1 mole of solute divided by 1 liter. I have a 1 molar solution. And that's exactly what we'd call this, a 1 molar solution. In fact is, I would write that down if I was to solve this. 1 mole divided by 1 liter, 1 liter, and I would get a 1 molar solution, and we use the capital M for molar, okay? That stands for molarity, okay? Our 1 molar solution. Also, because we're using units of moles per liter, the unit for a molar is also moles per liter. So you can use either unit. You can use the M for the unit, or you can use moles per liter for the unit of molarity, either way, okay? So this is our 1 molar solution. 1 mole dissolved in a liter of volume, okay? Total volume. There you go, all right? And let's look at some other real ones, okay? It's a little bit more. So here I have, for instance, 1 mole, okay? And again, 1 liter. And if I take a mole of a substance, I don't care what substance it is, this could be salt, 1 mole of salt, it could be 1 mole of sugar, it could be 1 mole of copper chloride, whatever it is, 1 mole of anything placed into 1 liter will give me a molar solution, okay, a 1 molar solution, all right, kind of idea. Okay, let's look at another possibility. Let's say I have another glassware here, okay? Now, if you read the label here, this is actually, it says 600, right? And that's to the very top, but the volume mark that you can actually fill this into is 500 milliliters, okay? So let's just kind of pretend that this is a 500 milliliter beaker, okay? So the total volume that we can fill in here is 500 milliliters, all right? Now, milliliters, we need this, if we're gonna use molarity, we need to convert this into liters. So this is really going to be 0.5 liters, right? It's gonna be half of a liter. And so let's say I put 0.5 moles of some substance. Again, this could be sugar, it could be sodium chloride, it could be copper chloride, something like that. And we're going to place that in there and it's going to dissolve, okay? So what would be the concentration, okay? Well, all you need to do is basically, again, plug that into my equation here. Let me clear this out. So my equation would show that I have 0.5, right? 0.5 moles of something dissolved in what? 0.5 liters is what we said. Because remember, this is 500 milliliters, but it has to be in liters to get our molarity correct. So 0.5 divided by 0.5 is what? 1 molar. So this is also a 1 molar solution once all said and done. Or again, we could put units of moles per liter as well. Okay. Well, let's try another one. What about something like this? We have, again, 500 milliliters. Okay, so let me clear this. We have 500 milliliters, and this time I'm going to put a mole in there. Okay, so I'm going to put 1 mole of some substance, and it's going to dissolve it. Okay, so let's do the calculation for that. So 1 mole, right, divided by what's the total volume is 0.5 liters. Again, it has to be in liters. So 1 divided by 0.5 is what? 1 divided by 0.5 is 2, right? 2. We have now a 2 molar solution, okay? Or 2 moles per liter, okay? Those would be the units, okay? So again, if I have a 500 milliliters, 500 milliliters is 0.5 liters, and I take my substance, which is 1 mole, and I put, oh, I just dropped my mole, and I put the 1 mole in there and dissolve it, then my solution concentration is going to be a 2 molar solution, or 2 moles per liter, okay, 1 liter. Hopefully that makes sense. All right, let's try one more. I'm going to clear this. All right, so let's say I have a smaller beaker. This is 250 milliliters. So let's say we fill this all the way up to 250 milliliters. And I'm going to take a 0.25 moles, whatever this might be. It could be salt, it could be sugar, it could be, you know, anything really. And I place it into my water. Okay, this won't fit all the way, but let's say it fits, and I dissolve it. Okay, so essentially what is my concentration? Okay, well, I would have, again, 0.25 moles divided by, so it's a 250 milliliters, so that's really in liters, 0.250 liters, okay? So then I could take my trusty calculator, or I can basically in my head, right, 0.2 divided by 0.2, or 0.25 divided by 0.25, right, it's just 1. So this is going to be a 1 molar solution as well, or again, you could use units of moles per liter, okay? So that's again how solution concentration works, is you take the number of moles of particles of the solute, okay, moles of solute, and you dissolve it in a certain volume of solvent or solution, the total volume. You divide the two and you get the concentration, solution concentration in molarity, okay? Hopefully that is clear. All right. So now what we got is some solutions here that we want to make some particle diagrams out of, right? And so we gotta think of this. And I'm gonna try to do my best of being able to draw here. Hopefully your drawings look a little bit better than mine. Okay, well, we're gonna do a salt solution. So we're putting in again sodium chloride. Okay, much what we saw with our particle diagram before. Remember that when we put salt in water, the water is going to dissolve the salt by surrounding the individual ions, the sodium ions and chlorine ions. So let's start with our middle solution. Okay, let's pretend that the volume here in each one of these beakers is 1 liter. Okay, so keep that in mind, that the volume here, I'll put the volume here for each one of these beakers is 1 liter, okay? Now, if I have a 1 molar solution and I was to draw a particle diagram, it might look something like this. So I'm gonna take my sodium ions, remember they're positively charged. There's a sodium, and here's a negatively charged anion, that would be chlorine. And let's say we have another sodium here. And then we have a negative charge here, okay, like so. And then what we're gonna do is we're gonna surround these ions by water molecules. And remember that the oxygens in water are attracted to the positive charge, okay? So essentially what I'm gonna do here is just create some water molecules and just show these attractions. I'm gonna put these little dots here to show the attraction, okay? And I probably should have more water molecules. You can fill in more water molecules. Just make sure that the water molecules are surrounding those ions, okay? And then for the negative ones, it's gonna be the hydrogen, right? Surrounded. So there's my oxygen, my hydrogens. That's not a very good one. Let me erase this one. Not easy to draw with this. All right, so we're gonna put my oxygen. There we go, and there's my hydrogen. Again, all you're doing is in your particle model, just put some water molecules around those ions, just surround them. And the same thing here, right? You're gonna draw those and so forth. I know this is taking some time here. Hopefully your drawings are much faster. Okay, and so forth. You know, you get the idea. We're just drawing these down. Okay, and surrounding these ions. The hydrogens are attracted to the negative charge, and the oxygens are attracted to the positive charge. Okay, so basically what we have here is 4 particles indicated that are surrounded by water molecules, okay? So if this represented 1 mole, what would a half a mole of salt solution look like? Well, you would see half the number of particles in your diagram, right? Because since this is a full mole per liter, or molar solution, this should have half the number of moles per liter. So here I would just have maybe 1 positive and 1 negative ion. So I'd have half the number of ions and surrounded by water molecules. So, boy, these are awful drawings. So again, just show that you have these water molecules. The big thing is to have the right ratio amounts, right? Because this is half, this should be double than what you have over here. Okay, here's a hydrogen. Here's a hydrogen. All right, hydrogen. All right, you get the idea. All right, so if this is a full mole and this is a half of a molar solution, and then we go to a 2 molar solution, what would you expect here? Hopefully you would say that it would be twice the number of moles in the 2 molar solution than in the 1 molar solution. So we would have positive ions, say a negative ion over here, positive ion, negative ion, say here, positive ion, negative ion. Let's see, I need 4, right? So negative, and then maybe another positive over here. Anyway, the idea is that I should have twice the number of moles of salt than I have in the 1 molar. And then these would all be surrounded by water molecules. So just in your picture, just draw a bunch of water molecules surrounding those ions correctly. Remember that the oxygen is attracted to the positive, and then over here, the hydrogens are attracted to the negative. Okay, and we'll get into more of what that means a little bit later. Again, we're just kind of giving you the basics for right now. Okay, so there's your salt solution drawings. Hopefully yours look much better than mine. All right, so the last thing we're going to do is, with this first video, is essentially solve some molarity problems. So in your study guide, you have some molarity problems that we're going to basically use the equation, molarity equation for. So, oops, back. So remember, molarity is equal to the number of moles of particles dissolved in the volume of solution, and it has to be in units of liters, okay? So that's the equation we're gonna use. So let's look at number 1. It says in your study guide, follow along with me, it says that you have a 1 molar solution, or sorry, 1 moles of potassium, so 1 moles of potassium chloride, okay? You know what? It might be better if we just go to the board and do this, right? So, you know, that's what I'm going to do. I'm just going to go right to the board and do that here on the board, these problems, okay? And then you can follow along with me. So when we reset this up, I think this might be easier to do. All right. So I have my study guide. So this might speed things up. So I got 10 moles of potassium chloride, right? And I'm going to place that in 750 milliliters of solution. It's probably water is our solvent here, okay? And they want to know what the molarity is. So this should be simple. Take 10 moles of potassium chloride, dissolve it in 0.750 liters. Remember, it has to be in liters, so I just convert my milliliters into the liters, and I get a 1.3 molar potassium chloride solution. All right, now sig figs are important here. Since I'm dividing 2 significant figures by 3 significant figures, my answer should have 2 significant figures in there. So don't forget, significant figures always needs to be in play here, okay? So that's number 1 on my study guide. What about number 2? Well, number 2 says I have 0.05, 0.50 moles of magnesium chloride. And I'm going to place that in 1.5 liters of solution. So this is even easier. So I'm just going to find the molarity of this by taking 0.50 moles of magnesium chloride, dissolve it in 0.5 liters of solution, and that is going to give me a 0.33 molar solution of magnesium chloride, okay? Or I could look at it as 0.33 moles per liter of magnesium chloride, okay? I can write the units either way, moles per liter or molarity, okay? And you're gonna see it written in either way, so make sure you're aware of that, okay? All right, so that's problem number 1 and number 2. I'm gonna erase my board here. Okay, 3. I have 400 grams of what? Copper sulfate. And I'm going to place 400 grams in 4.00 liters of solution. Okay, now I cannot find molarity from grams. I need molarity from moles. So what I have to do is convert my grams into moles, okay? So I'm going to do that, 400 grams of copper sulfate over 1 using dimensional analysis. I will do so, but I need the molar mass of copper sulfate. So you have to calculate the molar mass, all right? Well, I've done that, and I found that the molar mass is 159.62 grams per mole, okay, of copper sulfate. So when I do my calculation, I get 3 moles of copper sulfate, all right? So again, I've kind of already done this step for you where I've calculated the molar mass. You're going to have to do that in a problem like this if they give you the mass instead of the moles. All right, so now I have the moles. Now I can find my molarity. So I can take 3 moles of copper sulfate and divide that by 4 liters, right? 4.00 liters. And I get a solution of molarity of my solution as 0.8 molars to correct significant figures, copper sulfate, okay? So that is number 3 in your study guide, okay? So let's do 4. we have mass again. We got 0.060 grams of NaHCO3. That's sodium bicarbonate. And we have 1,500 milliliters, right, of solution. So again, I need to convert my mass to find the molarity. I got to convert, hopefully you see that. I got to convert my mass into moles. So I'm going to take 0.060 grams of sodium bicarbonate, set up my dimension analysis problem. I already found the molar mass of that, which is 83.00 grams to 1 mole of sodium bicarbonate. And that gives me moles of, in scientific notations, because it's really small, 7.2 times 10 to the minus 4 molarity, or moles, not molarity, moles, okay, of sodium bicarbonate. All right, so now I'm going to find my molarity by taking 7.2 times 10 to the minus 4 moles of sodium bicarbonate, and I'm going to divide that by my volume. But my volume, again, has to be in liters, so that's 1.5 liters. And so by dividing those two, I'm going to get 4.8 times 10 to the minus 4 molar solution of sodium bicarbonate solution. Okay, and that's going to be my answer. Again, this to number 4. Okay, number 4. Right? Hopefully this is making sense. I know I'm going through this pretty quick. I don't think that's the hardest part, is just converting the grams into moles and then divide by the volume. Okay, the moles by the volume to get the molarity. Okay. All right, let's do number 5. Okay. Now, number 5 is a little different, because now they give you the molarity and they give you the volume, and they want to find the mass. Okay. So they say that we have 200 milliliters of a solution that's 2.5 molar. Okay. And they tell us that it's a potassium carbonate. Okay. Potassium carbonate. That's the chemical formula for potassium carbonate. All right, now they want to know, well, if I have this concentration, then how many grams of potassium carbonate did I dissolve in the 200 milliliters? That's what they're asking for. Okay, so remember, if I had a bottle of potassium carbonate, I pour that into 200 milliliters of water. Okay, how much mass did I actually pour in there? That's what they're asking. So I need to find mass. So I need to take my molarity, and remember, molarity is equal to moles over volume in liters. Okay, so I manipulate this equation to find the number of moles, because I cannot find mass unless I know the number of moles. So the molarity times the volume, again in liters, is equal to the number of moles. So all I'm going to do is take my molarity, 2.5 molar, multiply my volume in liters of 0.200 liters, and that will give me my moles of 0.50 moles of K2CO3. Okay? Now I know the number of moles. So now I just have to convert that to mass. So 0.50 moles of potassium carbonate. Using my dimensional analysis, I need the molar mass of potassium carbonate, which I found was 138.21 grams per 1 mole. Okay, and that gave me an answer, once I got rid of the moles, of 69 grams of potassium carbonate. And that would be my final answer for number 5. Okay, so here's some here's 5 example problems that I've gone through with you. You may want to go back and review those example problems, okay? But what I want to do is pause this video for a minute and go ahead and solve the last 2, 6 and 7, and then turn the video back on, and I will have the answers for you as I erase the board and everything, okay? So go ahead and solve those last 2 problems. All right, hopefully you've solved those last 2 problems now. So the answer to number 6 would be 3.51 molar, and that would be for Fe2, Cl2, okay? And yes, I know they didn't give you the formula for Fe, for iron chloride, essentially. But if you need to go back and make some changes, that's what the chemical formula is, okay? For number 7, the answer would be 816 grams of copper fluoride. And that's the chemical formula for copper fluoride. Again, if you didn't get this answer because you didn't have their proper formula, then go back and retry it again now with the proper formula and check out your answer. See if you get it. Okay, on that. All right, so there we go. We've learned what a solution is. We've learned what the components of a solution, solute and a solvent, parts of a solution. We've looked at some particle diagrams of dissolving a salt in water and creating that particle diagram solution. We've looked at molarity and molarity concentrations, what it is, and how to solve problems using molarity concentrations. So that is it for this first video on solutions. So make sure that you rewatch this. If you need to, study your notes and then watch video 2, and then you should be done with this lesson. All right, so that's it for right now.